going to record. It is super similar to the heads tails because it's still a 50% chance. And we had 3 heads and 3 tails. So I did this triangle or this tree diagram up and down. We could have done it sideways like up here. It's really up to you, whatever kind of fits what you prefer. So again, this is first child, second child, and their third child down here. So if we just follow the tree, I'll work from left to right. So they could have had 3 boys, which sounds absolutely terrible. My son is wild. Oh my gosh. My daughter is just so different. And by different, I mean way better. Oh my goodness. All right. Anyways, so we've got boy, boy, girl. Should be more manageable. And then that's the end of like boy, boy. And so now I move down the tree a little bit to boy, girl, boy. And then it looks like it's boy, girl, girl. Side note, I love my son. I just love my daughter a whole lot more, I think. That's not too mean. So then we've got girl, boy, boy. Nah, he's great too. And then it looks like boy, girl, or sorry, girl, boy, girl. Which that's what we're hoping for this next time around. We'll see what happens. And then girl, girl, boy. Sorry about the stylus to keep sticking. And then girl, girl, girl. Curious what this chat's saying. Boys aren't bad. My son he's still great, but just a different. And my daughter's only 3. So, like, what do I know about, teenagers and, oh gosh, teenage girls. Yeah, I don't know. We'll see how that goes. I'll let you guys know in about 10 years. So again, that's our sample space. And essentially, like, the questions could be something like, what's the probability of having 2 girls at any order? You would just pick any that have 2 G's. Or what's the probability of having 3 girls? There's only one that has GGG, so it'd be 1 out of 8. That's kind of why we do the tree there. Fun. That's super fun. Yeah, birthdays are so fun. Sorry, I'm reading the chat. Oh my goodness, Christine. Ooh, that is a lot. We'll see where we stop. My wife wants to have 4 kids, so we'll see what happens, I guess. All right, so I remember this happened last year too. I didn't like how this ended up on 2 different pages. So I'm gonna screenshot this sample space, bring it down to the top here. Also, sorry, I don't mean to just talk about math all the time. I just want to be mindful of your guys' time. Again, if we were in a normal setting, it wouldn't just be, it would be, you'd probably feel more connected than over Zoom here. So sorry if I should be connecting more, but yeah, whatever. I'm gonna stop talking about that. All right. So if we are trying to find a family with 3 children who will have exactly 2 boys, so it looks like we can't have boy, boy, boy. We could have boy, boy, girl. Could have boy, girl, boy. Could have a girl, then 2 boys. I think that's it there. So it looks like there would be a 3 out of 8 shot to have exactly 2 boys. From there, if I erase my red X's and circles, probability that they will have at least 2 girls. So no, 2 girls. Nope. 2 girls. 2 girls, and 3 girls, which is at least 2. So that looks like that would be a 4 out of 8 shot. So it looks like, oh, but our probability is different. So, okay, so I was like going to think about, okay, what's the odds that we're going to have a girl next? It's different when you have like, it's different when it already happened. That's called conditional probability. Like conditional probability, I've already had a girl and I've already had a boy. So that probability is different than, we're going to talk about that later, but that's different than this right here, where it's like, what if this happened? This is like a hypothetical, like you don't know whether or not they had a boy first or a girl first. So that's probably worth noting there. Like for you guys to say, oh, you have if we really want a girl next, it's not a 1 in 8 shot of having a girl next. Well, it's a 50-50 shot. So whatever. When you're asking like when things have already happened, that probability is a little bit different. Okay, so we're trying to find the probability. Am I muted? Okay. At least one boy and at least one girl. So essentially, I think that's everything that's not the two ends of boy, boy, boy and girl, girl, girl. And so basically, you just want to avoid having only the one gender children. And so that would be 6 out of 8. Which if you reduce that down, they both can get divided by 2, which would be 3 and 4. Alrighty, moving right along here. Okay, so this is again where the tree diagram, in my opinion, is pretty helpful because it's a lot easier to see like what's happening. And so essentially it says a coin is flipped first. And so you could have a head or you could have a tail. And then after that, they rolled a 6-sided die. So you could have a head and then a 1, then a 2, 3, 4, 5, and 6. Same thing, you could do a tail and then 1, 2, 3, 4, 5, and 6. And like I said, the tree diagram is more just for you. Like, don't get all concerned about it being the perfect. Like if you can read it, that's all that really matters. Because like you're not going to draw one like on your test for me to grade. Like you would draw one so that you can answer it, something like this, something like H1. So if we're trying to list the whole sample space, you'd have H1, H2, H3, H4, H5, H6, and then T1, T2, T3, T4, T5, and T6. So again, there is a difference between what I just wrote in blue and just writing H, T, and then 1, 2, 3, 4, 5, 6. Again, that's a common mistake that people have. The sample space is like, given the specific scenario, what could happen? I could roll a head and a 1. I could roll a tail and a 6. You could argue that, okay, that's in my sample space if I just say HT and then 1, 2, 3, 4, 5, 6, but they want to know like the specific outcome. So that's why we were like, what's in blue right there. So then it says, what's the probability of getting a head on the coin and an even number on the die? So it looks like that would be H2, H4, and H6. So that would be 3 out of, I believe there's 12 things in blue there. So you'd have a 3 out of 12 shot of that happening, which would be 1 out of 4. reducing that down. What's the probability of getting a tails or an even number? So tails would be all of these guys there. And then even numbers, there's H6, H4, H2. And so that would be, it looks like 9 out of 12 possibilities, which again, if you reduce that down, that would give you 3 out of 4. So again, the tree diagram might seem kind of dumb and maybe not necessary, but it makes the actual answering of the question go like way quicker. So, you know, it's not going to say, like, you're not going to have to show the tree diagram. Like, you don't have to use it if you don't want to, but it might be easier to get all the possible outcomes in your sample space there. So tables could also work. We could have been doing that this whole time. I think I just feel like I mess them up a lot of the time. So I don't really use the table much, but especially if it's given to you like this, that's really nice. And so this is just basically breaking down a deck of cards into the 4 suits, which is on the left, and the numbers and letters, which is the top. This is calling ace low in the scenario here, treating ace as a 1. And then 11, 12, and 13 would be the jack, queen, king. Okay. And so there's 52 total cards. And so it says, what's the probability of drawing a jack? So I'd go over to my table, and it looks like there are 4 jacks. So it would just be a 4 out of 52. Notice this is different than asking like, what's the probability of drawing a jack and another jack? That would be something else, which we'll cover later today. So what's the probability of drawing a 3 or a diamond? So if we go to the 3s, there's these 4 3s right here. And then there's this whole row of diamonds right there, which 13 diamonds total. And a lot of people want to just do 13 plus 4. But if you do that, you're repeating the 3 of diamonds twice. So it's really just going to be 13 plus 3. You could have done 4 plus 12. It's going to be the same thing, all out of 52, making sure you don't repeat twice that 3 of diamonds there, giving you 16 out of 52 as your possibility. If you reduce that down, you can divide both of those by 2, which would be 8 and 26. Those both can get divided by 2 again, which would be 4 and 13. 13's prime. So that's how we know we're done reducing our fraction down. Oh man, I love cards. It's like such math teacher nerdiness. And I hate that it's like super stereotypical, but I love playing cards. It's so fun. So I said I don't like tables, and the next question has us make a table, which is great. So we've got our 2 dice, sorry. And we've got 1 red and 1 green, and then we're always going to roll that red die first. And so basically wants us to count up the possible scenarios of what could happen. So it wants us to look at the sum as well. So if you look at this part down here, it says the sum of 2 dice are given as the total. And so a 1 and a 3 would be called a 4, which is kind of normal when you're rolling 2 dice. But just thought that's worth mentioning. So if we continue with this pattern here, you could have rolled a 1 in red and then a 4 in green, a 1 in red and a 5 in green, and a 1 in 6. Sorry, a 1 in red and a 6 in green. And so if they've got this in the answer key, I don't know if they do. They don't. It's pretty lame. I'm trying to figure out if you guys want me to type all this out, to write all this out. Um,
In the
hmm.
homework, when you do it, it gives it for you.
Oh, that's great. Okay. So,
Just so
yes. So that means that I will copy and paste this just for your honor, your guys' time. And I'm sure people are, oh, last year I didn't even do it. Maybe I did live. Let's do this. Remember, I gave you guys the key for a couple of reasons. One, because you guys, it's nice to have it. And also, if I make a mistake, you guys can catch it too, which definitely happens. As you remember last week, I was on the struggle bus there with some of the financial stuff. Okay, so that's our table, saving us some time. So rolling an 8, it looks like you could have 4 and 4. And a lot of times the sums, you kind of just go off the diagonals. You could have 3 and 5, 6 and 2. And so it looks like you've got, is there any others that would be 8? I think that might be it. Those 5 out of 36 total, because it's 6 by 6, would be the odds of you rolling an 8. So rolling doubles here, it looks like the only doubles, again, traveling along the diagonal is going to be really helpful for this table here, is these guys on this main diagonal. So that looks like there's 6 of those. So 6 out of 36, which reducing that down, you could do 3 and 18. Oh, see, my thing keeps catching. Don't like that. And then those can both get divided by 3, which would be 1 and 6. And now this is the last one, is which is usually how it goes, the more frustrating one. Rolling less than 5. And so that looks like you're up there for those 3. Those 2 there, and then the 2 and 2 right there. Because everything else around, when I'm circling in purple right here, this stuff is all equal to 5. And then everything after that is bigger than 5. So it looks like just what we have there in green is what we want. So if you count that up, that looks like that is 6 boxes. So 6 out of 36, which would reduce down to 1/6, as you can see in the previous part B. Ooh, this next part is interesting. I always think about this next part when I'm trying to figure out a code for something. Like, I was just borrowing a friend's a wet saw, if anybody knows what that is, for cutting some tile. And I had to put in this code on his garage door, and it's kind of crazy how many different numbers can happen with just 9 digits. So this is kind of what that's getting at here. And so essentially, you just multiply when this says K1, K2, K3, Kn. That just means you just multiply together how many different kinds of each thing there is. And so this paint situation here, hopefully that'll make some sense when I say this in the paint situation. So you could have a red latex flat outdoor paint, and you could have a red latex flat indoor paint. And now you're done using flat and outdoor. So I'm going to keep red latex semi-gloss outdoor. red latex semi-gloss indoor, red latex high gloss outdoor, and then red latex high gloss indoor. Notice we haven't even switched to oil yet. And there's just a lot of possible scenarios that could be here. And that would have just been for red. And so to list all that out in a sample space, you would have done like R, L, F, O, R, L, F, I, R, L, S, O, R, L, S, I, R, L, H, O, R, L, H, I. It just would get crazy. There's just so much going on there. So what's nice is there's this little rule, this counting principle is what it's called, where there are 7 colors, 2 types, 3 textures, and 2 uses there. And so the how many different kinds can happen from you just multiply all those things together. And that's essentially the shortcut for how many different kinds there are. So when you multiply all those together, you get 84. And those would essentially be your Ks. Like this would be K1, K2, K3, and K4. Okay. A lot of times, yep. So this next one's getting into a code, which is what I was talking about from today. So even with only digits 1 through 5, it's asking how many 3-digit codes are possible if the digits can be repeated. So if you just like, you could have like 111, you could have 112, 113, 114, 115. And so that's only taken into account a situation where you had 1 and then a number. So like if you had 121, 122, 123, 124, 125, this would take forever. And so essentially there's 3 digits and you just want to multiply together however many could happen on each digit. So there's 5 possible for the first digit, 5 possible for the second, and 5 possible for the third. And when you multiply those all together, you get 125 possible combinations. So it kind of seems like too good to be true. Like, can I really have 125 possible combinations? I started to list it out in purple over there. So if you don't believe me, feel free to list it out. There's a lot. So this counting principle really saves us a lot of time. So then it says how many 3-digit codes are possible if the digits cannot be repeated. So you've got a 3-digit code. You've got all 5 to work with the first one. And then you can't repeat them. So you only have 4 options for the next one. And then you can't repeat those. So you only have 3 options for the last one, which would multiply all those together to be 60. And so that's a little bit more realistic. Sometimes the part A is sometimes called without replacement. Or sorry, with replacement. My apologies. With replacement. And then part B would be something without replacement. So as you're kind of looking at examples, a lot of times they'll use the language with and without replacement. We're almost ready to our next break, just this next page, and then we'll take our next break here. Okay. And so we've got this banquet table with 8 dishes of food. There's 4 vegetarian and 4 meat dishes. And then they're not going to put 2 meats or 2 vegetarians next to each other. And so it says that a vegetarian has to go first. So it's going to be vegetarian. And I'm going to draw 8 slots. So 1, 2, 3, 4, 5, 6, 7, 8. And it's got to go veggie. If vegetarian's first, then it's got to be meat, then veggie, meat, veggie, meat, veggie, meat. So it depends on what table you want, what end of the table you want to sit on. Okay. And so essentially you have 4 options for the vegetarian to start with. And then you have 4 options for the next meat. And then after that, we're just going to decrease by 1 because we already used up one of our trays. So the next V is 3. The next meat is 3. The next V is 2. The next meat is only 2 options. And then you've only got 1 vegetarian left, so it's got to go there. 1 meat left, so it's got to go there. And so you're going to actually multiply all those options together. Again, this is going to be a without replacement situation, because once it's set on the table, you can't set it on the table again. Like with replacement just wouldn't make sense in this scenario because there's only 8 dishes. You can't just like get another one. It's not. Yeah. Okay. I don't know what the scenario with food would be, but it would have to be a without replacement situation here. And when you multiply all those together, you get 576. Okay. So this next situation, it says we've got the passwords going on here. Each password is going to have 1 digit followed by 3 letters. And it's not, geez, it's not going to use G and then 2, 3, 4, and 5. So it's got 25 letters and 6 digits. If there's any tech people out there, and if there's like a reason to not use G, 2, 3, 4, and 5, feel free to let me know. And assume that the letters can be repeated. So that means it's with replacement. Okay. How many passwords can be used? So again, it said it's going to be a digit. Sorry. Yeah, 1 digit, and then it's going to be letter, letter, and letter. Okay. So we've got 6 digits. The digits aren't going to happen again. So it doesn't actually, there's not, the with replacement doesn't really affect us here. And then you've got 25 letters to pick from. And so since you could do something like 3, oh, can't do 3 because you're not allowed to, it says. Since you could do like 9 and then WWW, I'm going to take away the multiplication there. You can just use the 25 again 2 more times. But if that was not allowed, if you had to go like 9 WXY, like having 3 different letters, it would have been 25, 24, 23. So just kind of keep in mind the difference between with replacement and without replacement there. When you multiply all those together, I believe you get a huge number, 93,750. And that's why your people are trying to steal your information over the phone, because it's really hard to figure out these passwords because there's so many, even with this scenario where it's even pared down a little bit to 4 digits and not even all the letters and all the numbers.